Hi, Algebra 2 classes. So we're going to go ahead and continue section 2.6 here today. We're going to go ahead and pick up where the example, as you see here, suggests to graph f of x, which is equal to 3 times the absolute value of x minus 4. One of the things that I like to do whenever I'm graphing any function, for that matter, for the first time, is I like to make an xy table. So this xy table, as you guys can see here, it's got 5 x's, and then of course 5 y's with those x's. And what they did is they picked 0, a couple of positives, and a couple of negatives. Now I would have frankly picked 0 anyways, because 0, when I look at this original function, 0, when I set the quantity and the absolute value x equal to 0, that actually dictates the first coordinate of what we call the vertex. Okay, so 0 something, you can already see the graph done, but 0 something is in fact the x-coordinate of the vertex, and technically the y-coordinate of the vertex is right here. So 0, negative 4. And the reason you want to highlight to start with these absolute value graphs, to start with the vertex, is because from 0, negative 4, the function will either go up or down. In this case, you can see the function goes up. And it actually is kind of a V shape, as you can tell, as they obviously did all the other points and plotted them for you. I'm only going to require you guys to make 3 points when graphing an absolute value function. The first of which, of course, the vertex. I would definitely pick a point maybe 1 unit to the right, something like 1. 1 unit to the left, something like negative 1. So these 3 points, as I'm highlighting here, would be perfect. 1, negative 1, because when you plug in 1, the absolute value of 1 is 1, times 3 is 3, minus 4 is negative 1. When you plug in negative 1, the absolute value of negative 1 is 1, times 3, again 3, minus 4, negative 1. So those 3 points would be perfect, and I'll go ahead and just highlight as such. Draw your V shape as you see, and you're good. I'm going to go ahead and highlight the domain and range, because we will be asked to do that on tonight's homework. The domain of all absolute value functions is negative infinity to positive infinity, while the range, because my vertex point, here's why the vertex is so important. The vertex point is as low as this graph is going to go. In particular, the y-coordinate, as you see, is negative 4. So we're going to say our range is negative 4 to infinity. So it goes above negative 4, and it's also equal to negative 4, but not below it. Now, one of the things we're also going to want to do, and you can see as they describe in their answer, find several ordered pairs, graph the points, and connect them. You would expect the graph to look similar to its parent function. I'm going to go ahead and have you guys take a look quickly here at the parent function graph. The parent function, which I'm going to go ahead and quickly make an xy table for, using values like negative 1, 0, and 1. You can pick usually whatever you'd like, but this one in particular is definitely going to have a vertex at 0 something. That 0 comes from setting x equal to 0, but then of course, as I just noted, plus 0. So 0, 0 is your vertex, which would be right here on the graph. Plug in negative 1, the absolute value of which is 1. Plug in 1, the absolute value of which, of course, is 1. So I plot those 2 additional points. I've got enough to finalize my parent function graph. And then we can make a couple of other statements on top of this. So the black function is actually a transformed graph of the red, in which, if I simply go back, it won't take me very much to note this, but back to the original f of x, we can highlight that because of that number in front, the 3, we have what we call a vertical, if I could spell that correctly here, there we go, vertical stretch. Gave myself enough room too. A vertical stretch thanks to the fact that 3 is bigger than 1. And then we also have the negative 4, which we saw was the y-coordinate of the vertex. It's also telling us we're shifting down 4. So if we take the red function, vertically stretch it, but also shift down 4, we've got the black function. And we are going to talk more about transformed graphs down the road. But on this particular example, you can see quite nicely how it takes shape. What I'm going to go ahead and do is move on to example or problem 2. And we're going to go ahead and use all non-calculator techniques to start. We can use the graphing calculator to finish. So what I'll do, just like I did before, is I'll take the quantity inside the absolute value and set it equal to 0. This is going to tell us what the x-coordinate of the vertex is. And of course, if we subtract 1 and divide by 2, we get negative 1/2. So my xy table, when I set it up accordingly, I'll have negative 1/2 plug it in, and I'll actually squeeze in a plus 0 as well. But when you do plug in negative a half, you'll see it works out great, because negative a half times 2, that's negative 1, plus 1 is 0, plus 0, of course, 0. So that ends up having a y-coordinate of 0. I'm going to like to pick 2 more points, at least here. I like negative 1, and I like 0, particularly because negative a half falls between these two, and they're nice integer values. Plug in negative 1 times 2, that's negative 2, plus 1, that's negative 1, absolute value of which becomes positive 1. And then lastly, plug in 0, 0 times 2, 0 plus 1, 1, absolute value of which is 1. I have enough to graph, so let's do that. Negative 1, 1, negative a half, 0, and 0, 1. Graph your absolute value function, and we're good. The domain, like I was saying on the example, the domain will always be all reals on these graphs. The range, as we look again at the vertex being negative a half comma 0. The vertex, because the y-coordinate, I'll highlight as such, the y-coordinate is 0, will never go below technically 0, but only above it, can be equal to, it's going to look something like this. So the range would be 0 with a bracket to infinity. Now I'm going to go ahead and take a look at number 3. I know it was your homework over the weekend, but what I'd like to do is just kind of refresh your memories on what a stepwise function will take shape as. And because not everybody has a graphing calculator, I'd like everybody to at least see what it would look like on an XY table. And using an XY table, but also looking at the graphing calculator. I didn't graph number 2, but maybe I'll do that kind of back to back here. Continuing on with number 3. Let's go ahead and pick values. Particularly, I like negative 3. I like negative 2.5. I like negative 2, negative 1.5, negative 1, negative 0.50, 0.51. So as you can see here, I'm just kind of figuring out particular values, not just integer values, but also half increments in between those integers so that I can nicely come up with my steps, because this is going to be a stepwise function. So we plug in negative 3. The greatest integer for negative 3, in other words, what integer is less than or equal to negative 3? Well, that's negative 3. Plug it in, negative 3 plus 4, we've got 1. Plug in negative 2.5. What integer is less than or equal to negative 2.5? Well, that would be negative 3. Negative 3 plus 4, again, 1. Negative 2 is an integer, so we don't have to deal with that too much. Same with negative 1, same with 0, 1, and 2. So those are all going to be those respective values. But what about, again, those half increments? Negative 1.5, the integer that is less than or equal to negative 1.5 on a number line would be negative 2. Negative 0.5 would be negative 1. 0.5 would be 0. 1.5 would be 1. Now what I didn't do, and I'm just going to go ahead and fill in the blanks now because I didn't really complete things past the first 2 correctly. And I did that for a reason. I want you all to see how this is going to play out. If, again, you plugged in negative 2, you end up with negative 2. We can't forget to add 4, and so on. All of these needed to be plus 4. I'm kind of doing that as a finishing touch to kind of remind everybody that, well, you got to do that extra step. Finding the greatest integer is one thing. Doing the math in full is another. So when I do the math here, 4 minus 2, of course, 2. Again, 2, 3, 3, 4, 4, 5, 5, and then 6. And because I think one more increment would be wise, let's just go ahead and do 2.5, of which the greatest integer, again, the integer that is less than or equal to 2.5 would be 2. Adding 4, giving us or yielding 6. So if we start plotting these points, negative 3, 1, which is closed here. Negative 2.5, 1, right about there. Negative 2, 2, remember in green, those are my final y's, so negative 2, 2 puts me up here. So what that means then is that negative 2, 2, or correction, negative 2, 1, that's going to be an open circle. Similarly, if I say, what, negative 1.5, 2, I'm up here, and then I'm jumping to negative 1, 3. So that's going to go up here as a closed circle, which then means that that has to be open, and so on and so forth. I'll just continue. Closed, open, closed, open. My last value is a 2.5, comma 6. So 1, 2.5 puts me up at 6, so closed and then open. So this is our step function, as you can see, the domain of which will be all reals, and then the range of which, if you went ahead and looked at the answer key, which I'm going to go ahead and jump to right now, I just recently updated the sections, as you can see here at the top, Chapter 2 answers. This is available in the content library for all students in Algebra 2. So if you did want to see the answers for problem number 3, for example, you could do that. Just click on this tab and you would just scroll down and try to find section 2.6, which appears to be, here it is, page 17. So there you go, page 17. You can see if I go to view, I can zoom in a touch or two, and I can actually see the answers to both 2 and 3, and I can see the domain and range as well. They say that the domain is all reals, which I use my notation, negative infinity to infinity, and the range all integers, which I'll go ahead and literally just write all integers. This might be one of those exceptions in terms of domain and range where interval notation won't work. But I will accept, for example, the domain as you see, as usual for all reals, but the range is a little bit different. On the problem number 2 prior to that, we saw negative infinity to infinity and then 0 to infinity. And I believe if I go back, that's exactly what we saw. I'll zoom in a bit here to give you that perspective. And there it is, except that they, of course, don't use interval notation. Okay, so what I'm going to do to kind of finish things up here is I'm going to go to my graphing calculator. And I'm going to go ahead and type in the problem that I did for number 2, which, if you recall, was h of x equals the absolute value of 2x plus 1. Now, to get to the absolute value, I'm going to hit the math button after y equals, of course. Hit math, numbers. And then option number 1 is ABS, or absolute value. I'll type in 2x plus 1. You may see ABS pop up. That's okay. Just make sure you type in 2x plus 1 in parentheses then. And then I'll hit zoom, 6. Here comes the graph of the absolute value as we saw. We can do more analysis if we needed to. We could even look at the table if we needed to, hitting second graph. All right, various points, of course, are listed. That's pretty nice if you wanted to double check. We'll go ahead and graph number 3 as well. This is the step function, as we saw, f of x equals the greatest integer of x plus 4. To get to the greatest integer function, go back to y equals. This time I'll clear that function, math, numbers, and then option number 5. The greatest integer is that. I'll type in x, close the parentheses, because I'm only wanting the greatest integer for that, and then plus 4. Graph, and here comes your steps. Your graphing calculator is not going to show open circles on the far right ends of each respective step, but that's okay. Just to do a quick analysis, if we were to hit the trace button, and you can see when we plug in 0, we get 4. Scrolling to the right, noticing that the x values as they approach 1, and once they officially surpass 1, which they will right now, it jumps up to the next piece. So if you go back to your XY table and recall, we did in fact get 1, 5. Now I'm going to go ahead and move on. I want to wrap up with a problem of which we did do in class today, but one particular class did not get the opportunity to do so, and that's problem number 7. So problem number 7 on page 39, it says a stitch in time charges $40 per hour or any fraction thereof for labor. Draw a graph of the step function that represents this situation. So if you work no hours of labor or in any aspect of work, we're going to say 0 hours equals $0. And then if we take a look at 1 hour of labor, exactly $40. The number of hours in decimal form prior to that, excluding 40, which is going to be an open circle, you will get, in fact, $40. And then if we continue up the chart here, so to speak, open circle at 80, but then a solid line across to a closed circle at 2 hours, and so on and so forth. So similar to the step functions we've seen prior to this, except the open circle is on the left side of the step, while the closed circle is on the right side of the step. It makes sense that when you work increments that are either less than or equal to, let's say, 2 hours, for example. 2 hours or a little bit less than that, you're still going to get paid $80.